She made you answer two gods one day.
All right, the tests from yesterday have been graded and they're in online, so you can check and see how you did. I still have a few people though that need to take it, so you'll get it back once they're done. I'd say overall, yesterday was very, very good. I had, I think around the 7 to 10 range of people that actually had 100% yesterday. So it went very, very well. Very impressed. In the meantime, though, we're going to start our next unit, Unit 5, and we're going to be dealing with exponential functions. You may be familiar with these. Maybe you worked with them last year in Algebra 2. Maybe you've worked with exponential functions before in science or biology class. They're used a lot to model very, very fast growth, like bacteria growth or some type of population growth. So we're going to kind of get into those applications of exponential functions later in the unit. But much like how we explored rational functions, where we looked over a bunch of different properties and characteristics, we'll eventually be able to start with a graph and then write the equation, or I can give you the equation and you'll be able to draw the graph. Okay, that's our ultimate goal by the end of this unit, just like it was for rational functions. Before we start, though, to really dive into exponential equations and graphs and properties, we first have to be very familiar with exponent properties, because we're going to be manipulating these exponential functions, and if we can simplify them to a very easy form, it's just going to make our analysis that much easier to do. So we're going to just spend today and Friday, because tomorrow is our Zoom day, looking at properties of exponents. It's going to be a little throwback to Algebra 1, okay, so it's going to be a good review, but much like how we had to review factoring to help us with polynomials, we have to review these properties as well. So you might know them, you might not, but in the end I hope they kind of come back to us today and Friday. So just in terms of vocabulary, if I had 5 to the third, can we label by name what we would classify the 3 as and what we would classify the 5 as? If you have a little number kind of to the right top hand side of another number, what's that referred to as? Yeah? An exponent or a power, okay. I'm going to abbreviate because I'm a little out of room there. Okay, exponent or power. What about the 5? Sometimes we forget this one, yeah? The base, okay. So as we go through some of these examples, you might hear me say we have the same bases. Maybe we can subtract the exponents. Okay, we have to be familiar with what we're actually talking about. So I think, at least based off of first period, our first 3 properties of exponents we're really good with. Okay, we're really familiar with. The last 3, though, might be a little different or difficult for us because we're not too familiar with those ones, but we'll just see how this goes. So in general, okay, that's what we're going to do on the left-hand side. In general, we're going to write down the property, and then we'll take a look at an example that demonstrates that property. So can we think back to Algebra 1? If you have 2 of the same bases being multiplied together, what can we do with the exponents? Yeah, add them. Okay, so the 2 bases being multiplied together actually stays the same base. Okay, you don't do anything with that base. Much like how when you add or subtract fractions, you don't change the common denominator, it stays the same all the way through. That's what's going on here. Okay, the base doesn't change. You're only manipulating the powers or exponents. So if we add the exponents, we'll say m plus n. All right, so if we take a look at a number example, okay, throwing in some numbers here instead of just variables, notice how we're taking a base of 5 to some exponent times another base of 5 to some exponent. So the bases match, they're being multiplied together, which means we can simplify this by keeping the base the same, so we'll keep the 5, but then we're going to add the powers together. Now notice how these powers are a little bit more involved than just 3 or m and n. We're going to start to have variables in here that we're going to have to be careful with. So if we're going to add these together, maybe we'll just add like terms. So 2x plus negative 4x, we could say is negative 2x. And then if we add negative 3 and 5, we'll have 2. All right, so I'd say that's pretty good. Our ultimate goal with these simplifications is to get one base to one power. Okay, we'll see how far we can get with these in the end. What about the second one? This time we have the same base, but we are dividing the bases. So can we think about what we would do with the powers? Yeah? Subtract them. Okay, so we're going to keep the base the same. And we have to be careful though with subtraction because order matters when you subtract. 5 minus 3 is different from 3 minus 5. So the question is, how do we subtract the powers? Do we do top power minus bottom or bottom minus top? Top minus bottom. Okay, m minus n. All right, so our number example though is really starting to amp it up now because we have kind of multiple properties going on in here. If you look at it, all of the bases are the same, which is wonderful because that means we can use some properties to our advantage. However, we have bases in the top that are being multiplied together and bases in the bottom being multiplied together. So we do have some of this first property showing up. Maybe we'll simplify the top and the bottom separately, and then we'll kind of see how this division property can be used. So if we just work up top, we're going to go ahead and add the powers because we're multiplying the bases. That'll give us 4x plus 4. If we do the same property on the bottom by adding the exponents, we'll have 3x minus 4. So now it looks very familiar to this division property with exponents. So the bases are the same. Okay, we'll keep that base. And then we're going to subtract the powers by doing the top power minus the bottom. So using some like terms, we'll do 4x minus 3x. So that would be 1x. And then we need 4 minus negative 4, which would change to a plus 4, so this would be 8. Okay, so notice how in the end we're able to simplify it to one base raised to one exponent. We doing okay so far? Coming back to us? Maybe never left? Okay. What about the third one? What if we have a power being raised to a power? Can we think about how we would combine those? Yeah? Multiply them. Good. So a to the m times n. All right, so in our number example, this is kind of showing up in the first term. Notice how we have a power of 3 being raised to a power of x minus 2. So a power to a power will multiply those together. Our new power would be 3x minus 6. Okay, you kind of have to distribute that 3. We still have another term to kind of consider here. So after we simplify the first term, now notice how we're multiplying two of the same bases together. So this is kind of moving us back to this first property we talked about where we can add the powers. So we'll keep the base. Adding the like terms, we'll have an x and a minus 4. All right, so I'm pretty sure those first 3 properties are ones that we're really familiar with or the ones that we kind of use the most in our mathematical studies or problems. The last three are a little different. Okay, these are the ones that I see students kind of struggle with the most. I'm pretty sure you've been exposed to them before, but like I said, they're the ones that might not be as common sense or the ones that we struggle with the most. What if we have a negative power? How does that affect the base? Yeah?
Supposed to put it in the denominator.
You move it to the denominator. So this would be 1 over a to the n. Okay? The negative power does not change the base to a negative number. Okay? The negative power just tells you you can move it in a fraction. So if you have a negative power in the top, you can move it to the bottom. If you have a negative power in the bottom, you can move it to the top. Okay, it's just telling you can do a little switcheroo. All right, so if we take a look at our example here, we don't really have a negative power per se, but we do have a negative on the x, which maybe we can factor out. So maybe we'll pull out a -1, and we'll be left with 2x minus 2. So notice how we have 3 to a -1 power. That means we can move this 3 to the negative first to the bottom of a fraction. So this would really be 1 over 3 to the first, but 3 to the first is just 3 if you want to leave it the same. So this piece can be changed, okay, flipped because of the negative power, and this 2x minus 2 we haven't really touched, so it'll stay as an exponent. Okay, this is a good example, I think, for us to realize that the base might not always be a whole number. Okay, notice how the base in this case is a 1/3. I know in all the other ones it was like a 2 or a 5, but sometimes your base can be a fraction. Okay, we're going to see that quite a bit in this unit. All right, what if we have a base to 0? Yeah? It's always 1, okay? I don't care if it's 10 to the 0, 2 to the 0, it's always going to be 1. Now, we could probably anticipate that our example here is going to end up having a 0 power just because it's listed next to this property, but let's see if we can get it to be that. When you look at this example, though, we kind of have to be strategic or a little aware that some of the bases match, but not all of them. Okay, we have 2's that match, but this base is a 4. Can we be a little tricky in how we can get all the bases to be the same? Yeah?
If you half the base and multiply the exponent by 2, it's the same number.
It's the same number. Okay, so let's think. Is there any way, notice how these 2's already match. We got to think about, is there a way that we can rewrite the number 4 as 2 to a power? 2 to what power gives you 4? The second power, okay? So notice how I'm being a little strategic. Instead of leaving this as a 4, I'm going to change it to a base of 2. That way, it matches the other bases of 2, and we can eventually use properties. Now, this is just rewriting the base of 4. I still have the power of 2x plus 2. Now, River kind of mentioned everything in one step here, but notice how when we rewrite 4 as 2 squared, we now have a property showing up. We have that power to a power. So that means we can multiply those powers together. That'd be 4x plus 4. And now that all the bases match, we can go through and use some of our other properties. Notice in the numerator, we're multiplying the same base, so we should be able to add the powers. Combining like terms would give us 5x plus 3. And that's exactly what we have left in the bottom. So can we think about if we have 2 to the 5x plus 3 divided by itself, what that would simplify to? Yeah? 1. Anything divided by itself is 1. So we know that this should be 1. Okay, but let's see how that relates back to this property. Notice how we are dividing two of the same bases together. So we can look back at number 2 up here, which tells us we should subtract the powers, top minus bottom. If we do 5x minus 5x, that's 0. 3 minus 3 is 0. So look, or notice rather, how the powers go away and we're left with nothing. So we know that 2 to the 0 should be 1. Okay, so you might be able to reason through it here that something's being divided by itself, but just in case you don't notice that, you can use a property to get that power to be 0. Okay, anything to the 0 power is 1. All right, the last one might be a little different. Are we familiar with how a fractional power operates, how that works? This is a little tricky. Maybe I'll do an example. If I had a to the 3/5, that's the same as the 5th root of a cubed. If I had a to the 5/2, that's the same as the square root of a to the 5th. Can we make a generic case? What if I had a to the m over n? Yeah. There we go. Okay. If you have a fractional power, the denominator of that power is the type of root that you have, and then the numerator is the power on the base, which is inside that root. Okay, might be a little new to us, maybe we're familiar with it or at least seen it before, but like I said, these last 3 are kind of the special ones that we tend to have trouble with. Okay, so a fractional power is signifying some type of root. All right, let's see if we can use that property for this example. Notice how everything is being square rooted. So instead of having that square root symbol there, I can change it to a power of a half. Okay, if we think about it, a to the 1/2 would be the square root of a to the 1st. Okay, so a square root is just signifying a power of a half. On the inside, we have 3 to the 2x plus 2 times 9 to the x minus 4. Now the bases don't match, so we cannot use any other properties to our advantage, but can we be strategic to get them to match? Is there a way I can rewrite the number 9 with a base of 3? Yeah.
3 squared.
3 squared. All right. Now, by rewriting 9 as 3 squared, we are creating another property that we could use. We have that power to a power. So if we multiply the powers, we'll get 3 to the 2x minus 8. Now that we strategically have the bases the same and we're multiplying them, we can add the powers together. So that would be 4x minus 4. And lastly, notice how we have a power being raised to a power. So we multiply those together, which would be a new power of 2x minus 2. Wait, this should be 6. My bad. So then this would be 3. All right, so in the process of trying to simplify something, you might actually create more properties you have to use. Notice how that was the case here when we rewrote 9 as 3 squared. Okay, we created a property of a power to a power that we would have to use. So sometimes in order to go forwards, you might have to create a little bit more work for yourself. But that's not saying we can't do it. Okay, it just might take us an extra step or an extra moment to eventually get there. Okay, how are we doing with these 6 properties? Okay, good. Okay, we're going to try some examples. Now, These are going to be a little bit more involved, perhaps. Okay, maybe they get more difficult or demanding as we go, but we'll see how these go. Let's take a look at number 1. Notice how everything on the inside of those parentheses is pretty simplified already. We have 1 base of x, 1 base of y, and 1 base of 3. But every single item inside those parentheses is being raised to a power of 3. So notice how this would be an example of a power to a power, because everything inside that parenthesis set has some type of power on it. What's the power on the 3? If you don't see it, it's understood to be a 1. Okay, so maybe you want to write that in there just in case. So if we use our power to a power property, we'd have to multiply the powers together. So this would create 3 to the 3rd if we do 1 times 3. Then we'd have x to the 9th if we do 3 times 3. And then y to the 15th if you do 5 times 3. Right. I'm not too sure if we can go any further with that in terms of our properties, but maybe we can rewrite something. Do we know what 3 cubed is? Because that's eventually just going to be a number anyway. 3 times 3 times 3? 27. Oh, that's a y. All right, there we go. Okay, sometimes though we might have to use more than one property. So moving on to 2, notice how we are multiplying some terms together. But if you think about your order of operations, parentheses and exponents come first. So we really should work on this second term initially, because we have that outside power of 3 that's kind of dictating something. So maybe we can do something with this term like we did with our first example. Okay, we have a power to a power. So this would be 2 to the 3rd, a to the 6th, b to the 9th. Right, so now that the outside power is gone, maybe we can start to actually multiply some of these items together. I have a to the 1st times a to the 6th. So by adding the powers, I'd have a to the 7th. I also have b squared times b to the 9th. So adding the powers, I'd have b to the 11th. Now for the numbers, notice how this base of 3 is different from that base of 2. So there's nothing we can do with the powers. Okay, we can't combine them in any way because the bases are different. But since these are numbered values, maybe we can multiply the numbers together. So really, 2 cubed is 8, and 3 to the 1st is 3. So can I take 3 times 8? That would be 24. Okay, so you can't do anything with the powers, but you can do something with the overall number value itself, okay, when you're multiplying them together in this instance. We doing okay so far? Okay. What about 13? Can we simplify the numbers first? Can we do 12 divided by 15? Three goes in? Yeah. 4/5. Okay, so we'll simplify the numbers. What about the variables? A to the 3rd divided by a to the 5th. If you used a property, how would it work? Maybe some of you can go straight to the answer by looking at the powers themselves. You have an idea, Carter? Yeah. A over 2? Is that what you said? Yeah. A over 2. I like the A and I like the 2, but I don't think it's A over 2. I think it's A squared. If you do, let's think about this. If we are dividing the same base we should be subtracting the powers. So 3 minus 5 would give us a negative 2. But using another property, if we have a negative power, that means we can flip it. So this would be 1 over a squared. So it seems like in our final fraction, we should have an a squared left on the bottom. Okay, you don't have to worry about the 1 as a placeholder because we already have a 4 up top in that fraction. All right, let's get good here. Taking a look at 4. We have a massive fraction all being squared. So think about your orders of operation. Parentheses come first. And normally we simplify everything inside the parentheses first, right? Parentheses come first, everything on the inside. So can we simplify the inside of this fraction at all? Can we do 3 divided by 5? Can we simplify that? Probably not. Okay. What about the a's? A squared over a to the first. I'm left over with 1a, and where is it? Yeah, up top. What about b cubed over b squared? I'm left with 1b, and where is it? Up top, right? Because you have more b's up top than you do on the bottom. So you're going to be left with the ones up top. All right, so we simplified the inside. We still have to do the power though. Okay, that exponent comes next. So absolutely everything inside that parenthesis is being raised to the power of 2. So I should have 3 squared, a squared, b squared over 5 squared. And if I decide to simplify some of the numbers, this would be 9 a squared b squared over 25. Do you guys think you can try 5? Kind of similar to the one we just did. This time just x's and y's instead of a's and b's. Go ahead and try 5, see how you do. All right, let's check it out. Depending on what you felt like doing first, okay, in terms of your properties, you could have approached this many different ways, but ultimately we all should have ended up with the same result. So I'm curious what you simplified first. How did you first approach this example? Do I need my sticks? You have a shot? Yeah.
Do you know the whole process or just the answer?
Give me the first thing that you notice.
Okay, the first thing that I noticed. So, there's x's on y and y's on both top and bottom.
Okay.
So you can get 1 over x to the third, y to the fifth.
Okay. So let's take things individually here. So Travis decided to work on the inside first. Okay, think about order of operations, parentheses, insides comes first. So x squared divided by x to the third. You'd subtract the powers. Okay, 2 minus 5 is -3. But you can move that to the bottom of a fraction, so we would have a positive power of 3 on the bottom, okay, based on the x's. How'd you get y to the 5th, Travis?
I think I skipped a step. No, I didn't. Okay, so -3
Mm-hmm.
minus 2
Yep.
is -5.
-5.
And then, since it's -5, it should be on the bottom.
It'd be on the bottom, okay? So looking at the y's, subtracting the powers, -3 minus 2, -5 means it should be left on the bottom of a fraction. So what's left up top?
1.
1 is a placeholder. Good. Okay, so if you simplify the inside, get all the x's and y's to just one base, I like where this is leading us. Travis, do you want to keep going?
Sure, I guess.
Okay, what'd you do from there?
So then you multiply the 3 into the everything, like the third power.
Okay, so 1 to the -3rd, x to the -9th, y to the -15th.
Alright, so 1 to the -3rd.
Yep,
I moved that to the bottom because, I mean, it's going to be at the bottom anyway.
it's a negative power. Okay, so 1 to the 3rd moves to the bottom.
And then 1 to the 3rd is just 1, and then the x to the 9
Mhm.
and y to the 15 is going to be top. Is it negative?
They're negative. Okay, negative power does not always mean bottom. Negative power means move or switch. So if you have a negative power on the bottom, you can move it or switch it to the top. Okay, and like Travis said, 1 to the 3rd is just 1, so you don't really have to worry about that being there. And we have x to the 9th, y to the 15th. Yeah.
I did it a slightly different way. I don't know if it's correct.
How'd you do it? Mm-hmm.
So I did it like, I did the inside first, and I got x to the -3rd and y to the -5th, and then I multiplied both of those by -3. I got 9 in this time.
That would work as well. Okay, so instead of moving them to the bottom like Travis did, you decided to keep them negative, and then you did a power to a power, which got you the same way. Okay, there's always more than one way to do something. Okay, but as long as you use the properties correctly, you'll get the right answer in the end. Okay, looks good. How do we do? Could we get all of it? Some of it? Some of it? Okay. All right, let's try 6. Kind of similar setup to the previous ones. If you try to simplify the inside though, notice how 8 over 27 cannot simplify, and we only have x and y as the bases. We don't have any other ones that we would have to use a property for. So it looks like the inside of this fraction cannot be simplified. So then maybe we can move to the power on the outside. So this is another example, yet again, of a power to a power. We would have to rewrite this as 8 to the 2/3. And then for the x power, we'd have to multiply them together. 3 times 2/3 would just be 2, because the 3's would cancel. We'd do the same thing for the bottom. 27 to the 2/3. And then for the y variable, 6 times 2/3 would be 4. All right, now for the x and the y, the powers are pretty simple, but notice how for 8 and 27, the powers are still fractional. That means we should be able to rewrite this as a root. So what might 8 to the 2/3 look like as a root? Is it the square root of 8 to the 3rd or the cubed root of 8 squared? You kind of have two options. Cubed root, 8 squared. All right, and then for the bottom, this would be the cubed root of 27 squared. I'm curious if we can actually figure these out. Okay, let's try it. If you do 8 squared, that's 64. Can we take the cubed root of 64? What number times itself 3 times would give you 64? Yeah, 4. Okay, so 4x squared's left up top. Notice how if we did the same process for the bottom, this would get very ugly. Do we know what 27 squared is in our heads? Definitely not. Okay, so this is where you can be strategic. I need you to look at this, okay? You can be strategic. Instead of doing the power first and then the root, you could do the root first and then the power. Okay, it doesn't matter. Let's try that for this one. What's the cubed root of 27? 3. 3 squared? That's 9. Isn't that a lot simpler? Okay. That would also have worked if we did that for the 8 up top. The cubed root of 8 is 2. 2 squared is 4. Okay? So it doesn't matter which one you do first, as long as you do both. And then we're left with y to the 4th on the bottom. How are we doing? Okay? We're going to save the next 2 for tomorrow, and then we'll get into some other examples on Friday.
4x squared plus y to the negative 4. Mistakes bring out the minus 1 and 4 is the same.